Pluto has drawn closer to the other planets in an unexpected way, as its orbit crosses the paths of several nearby planets. Despite its small size and distant location, Pluto's orbit has been causing some concern among scientists and enthusiasts, particularly regarding its potential interaction with Neptune. Notable figures like Neil deGrasse Tyson and Michio Kaku have raised alarms about the implications of this unique event. But how did Pluto end up on a collision course with Neptune? And what might this mean for life on Earth? Once considered the ninth planet in our solar system, Pluto was reclassified as a dwarf planet due to its erratic orbit. However, Pluto remains fascinating and captivating for astronomers, particularly given its unusual orbital dynamics. Estimates by respected scientists such as Tyson and Kaku have highlighted concerns over Pluto's orbit possibly intersecting with Neptune's, suggesting a future alignment that could have significant consequences. Pluto's orbit is unique within our solar system, as it is not aligned with the ecliptic plane that most planets follow. Instead, Pluto's orbit is tilted at an angle of 17 degrees and is highly elliptical. This results in Pluto's distance from the Sun varying dramatically throughout its orbit. At its closest approach, Pluto comes within about 30 astronomical units, AU, of the Sun, while at its farthest, it is more than 39 Australian dollars away. This irregular orbit also brings Pluto into occasional proximity with Neptune, raising concerns about a potential collision between the two celestial bodies. Interestingly, although their orbits intersect, the likelihood of a direct collision is extremely low. This is due to a rare gravitational interaction between Pluto and Neptune that stabilizes their orbits. For about 20 years during each orbit, Pluto's path brings it closer to the Sun than Neptune, but they avoid colliding due to a resonance between their orbits. This resonance means that when Pluto crosses Neptune's orbit, the two bodies are always 90 degrees apart, preventing a direct collision. This gravitational dance between Pluto and Neptune highlights the dynamic nature of our solar system. Even though Pluto was once considered an isolated object in the far reaches of the solar system, its interactions with Neptune emphasize the interconnectedness of celestial bodies. These gravitational forces shape the paths of planets, moons, and dwarf planets, and the study of these interactions offers valuable insights into the workings of our solar system. Recent advancements in observational technology have allowed astronomers to track Pluto's movements with greater precision. This has led to a deeper understanding of its orbit and its potential impact on the stability of the outer solar system. While the possibility of an actual collision between Pluto and Neptune remains remote, the continued study of their orbits is essential for predicting future cosmic events. Despite its relatively small size and distant location, Pluto continues to captivate the imaginations of scientists and space enthusiasts alike. The question remains, why hasn't there been a collision between Pluto and Neptune? The answer lies in the intricate mechanics of their orbits, which are influenced by the gravitational pull of the larger planets in the solar system. The precise calculations needed to understand the interactions between Pluto, Neptune, and the Sun are complex, and even small changes in their velocities or positions can lead to significant shifts over long periods of time. To predict the future of Pluto's orbit, astronomers rely on sophisticated computer simulations that model its movements and interactions with other celestial objects. These simulations allow scientists to understand how small changes in Pluto's velocity or position could affect its long-term trajectory. Although these models suggest that Pluto's orbit is relatively stable over billions of years, they also reveal that even tiny perturbations can cause significant changes in its orbit. In conclusion, while Pluto's orbit may seem chaotic and unpredictable, the gravitational forces that govern the motions of celestial bodies work together to keep Pluto's path stable over long periods of time. Although the prospect of a collision with Neptune is unlikely, the study of Pluto's orbit continues to provide valuable insights into the complex dynamics of our solar system. The ongoing research into Pluto's movements will help us better understand the stability of the outer reaches of the solar system and the potential for future cosmic events. The orbit of Pluto is often seen as a valuable window into understanding the fate of other celestial bodies and the intricacies of gravitational interactions. By examining the complex gravitational relationships and orbital dynamics of objects like Pluto, we can improve future space missions, ensuring safer navigation through the solar system and anticipating potential risks. Such knowledge is crucial for planning missions to distant regions of our cosmic neighborhood. Michio Kaku emphasizes that the lessons learned from studying Pluto's orbit could be applied to exploring other celestial bodies, helping us to navigate and understand distant worlds. He often discusses the profound connection between celestial mechanics and theoretical physics, particularly how the interactions between planets, like the gravitational dance between Pluto and Neptune, are grounded in fundamental principles of physics. Kaku's work in theoretical physics, especially string theory, seeks to unravel these principles at their core. He suggests that by focusing on the complex dynamics of planetary orbits like Pluto's, we can gain insights into the fundamental laws governing the universe. Both Kaku and Neil deGrasse Tyson have speculated about the potential collision between celestial bodies, linking it to their theories about the universe. A collision between Pluto and Neptune, despite the vastness of space, could present a unique observational opportunity to further our understanding of string theory and other areas of theoretical physics. Such an event could generate extreme conditions of energy and gravity, offering valuable data on the behavior of fundamental particles and forces in extreme environments, an important consideration in string theory. The gravitational waves generated by such an impact would also provide significant insights into string theory's predictions regarding gravity and spacetime. While the direct impact on Earth may be minimal due to the distance from the outer planets, the scientific implications could be profound. Understanding events like this could deepen our knowledge of the fundamental nature of the universe, as described by string theory and other areas of theoretical physics. Pluto's unique characteristics, shaped by the gravitational forces of nearby planets like Neptune, highlight the intricate and dynamic nature of space. However, the universe still holds many secrets, and the three-body problem is just one of them. Researchers are considering various potential impacts that could further our exploration of the vast universe. Even though the likelihood of planets colliding in space is low, the gravitational interactions between planets can cause subtle shifts in their orbits. This phenomenon, known as the three-body problem, is seen in systems like the TRAPPIST-1 system, where 7 Earth-sized planets interact gravitationally, creating orbital resonances that could potentially destabilize a planet's orbit over time, possibly leading to a collision. Though such collisions are not imminent, scientists are closely monitoring these interactions to better understand how planets influence each other's orbits, particularly as they move closer together. The study of Pluto's orbit, its gravitational interactions, and potential collisions with Neptune provides insight into the complex and dynamic nature of planetary systems and theoretical physics. As we explore the intricacies of Pluto's path and its interactions with Neptune and other celestial bodies, it becomes evident that our solar system is far from static. Once considered a solitary object in the outer reaches, Pluto now reveals itself as part of a delicate gravitational dance that spans billions of kilometers and millions of years. The gravitational forces exerted by Neptune on Pluto are pivotal in shaping Pluto's orbit. Despite the vast distance between them, these two celestial bodies periodically approach one another due to the eccentricity of Pluto's orbit. Unlike the nearly circular orbits of the inner planets, Pluto's orbit is elongated, resembling more of an oval shape. This eccentric orbit leads to significant variations in Pluto's distance from the Sun throughout its roughly 248-year orbit. At its closest point to the Sun, perihelion, Pluto ventures within Neptune's orbit, coming closer than Neptune's average distance from the Sun, approximately 30 astronomical units. However, at its farthest point, aphelion, Pluto moves beyond Neptune's orbit, reaching over 49 astronomical units. This wide range of distances means that Pluto and Neptune's orbits cross at certain points, creating interesting gravitational interactions between the two bodies. These interactions are particularly fascinating because they demonstrate the delicate balance of forces within our solar system. While Neptune is much larger than Pluto, its gravitational influence on Pluto is still significant due to their occasional close encounters. These interactions subtly alter Pluto's orbit over time, guiding its path around the Sun. Additionally, Pluto's orbital plane is tilted at an angle of about 17 degrees relative to the ecliptic plane, the plane in which most of the planets orbit the Sun. This tilt adds another layer of complexity to Pluto's orbit, as it means Pluto's path through space is not perfectly aligned with the orbits of the major planets like Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, the unpredictability of space is difficult to comprehend, but studying phenomena like Pluto's orbit helps us understand more about how our solar system operates. Pluto's path reveals how orbits that seem unstable can be influenced and stabilized by gravity. This teaches us that the universe is full of surprises, and Pluto's orbit is a prime example of such eccentricity. Unlike most planets, Pluto's orbit is highly elliptical, meaning it is far from a perfect circle. Sometimes it even comes closer to the Sun than Neptune does. This creates an interesting dynamic because, despite their orbits crossing, the gravitational forces between Pluto and Neptune prevent a collision. Gravity, an invisible force, pulls objects toward each other, and though Pluto and Neptune appear to be on a collision course, their orbits are perfectly aligned to avoid this fate. This delicate balance of forces in Pluto's orbit shows how space can be full of unexpected events, even when things seem turbulent. By studying Pluto's orbit, scientists gain valuable insights into the mechanics of our solar system. The ongoing research expands our understanding of the universe and our place within it. If Pluto and Neptune were to collide, it would be a monumental event that could revolutionize our comprehension of the nearby planetary system. Despite the progress we've made in exploring space, the complexities of celestial bodies suggest that we still have much to learn. Pluto's orbit provides a model for understanding how planets interact, and how one planet's path can influence others in the system. Even though space is intricate, some scientists are concerned about the possibility of Pluto crashing into Neptune. While this seems unlikely, it still raises intriguing questions about the dynamics of our solar system. Neil deGrasse Tyson, a renowned astrophysicist, has often discussed Pluto's unique orbit. He proposes that Pluto should be reclassified as a dwarf planet, a designation that acknowledges its distinct status without undermining its importance in the study of space. Tyson believes that by continuing to explore and learn about celestial bodies like Pluto, we can better understand the complexities of space. He finds the unusual nature of Pluto's orbit to be a reminder that there is much we still don't know. Tyson also sees these discussions as an opportunity to engage the public in space science, emphasizing the importance of learning about and preserving the mysteries of our solar system. He works alongside other scientists to raise awareness about the potential dangers posed by Pluto's orbit. Though the chance of a collision between Pluto and Neptune is slim, Tyson points out that such an event would have far-reaching consequences for our entire solar system. The impact would release immense energy, potentially scattering debris across the solar system, and could alter Neptune's orbit and behavior as well. The famous theoretical physicist Michio Kaku has also weighed in on space exploration. He argues that understanding the future of space travel and the relationship between celestial mechanics and theoretical physics could unlock new areas of discovery. Kaku believes that studying the unique characteristics of orbits like Pluto's can help us understand the broader dynamics of our solar system and the universe.